there, let's talk about polar and non-polar molecules. So we got some rules we're going to follow, and they really depend on the electron geometry and the molecule geometry. So we need to be looking at the molecule geometry in order to do these polar and non-polar molecules. So when we're looking at something that's non-polar, we're looking for a molecule that is symmetrical. So I'll show you a few examples of what we mean by that. So symmetrical, that means same terminal atoms. Terminal means end, so the atoms on the ends, and no lone pairs. So the lone pairs automatically make the molecule geometry unsymmetrical. So what makes something polar, a molecule polar, is when you have an uneven distribution of electrons. You've got a more positive side and a more negative side. But if you have an equal distribution of electrons, then you're not going to have that one negative side, one positive side. It'll just be neutral. So for example, CO2, we've seen this one before. It's got double bonded O's. Now, O is more electronegative than C. If we look at our periodic table, we remember that increases to the right and up. So O is more electronegative than C. That means the electrons are going to go towards O. That's how we draw that. We draw this little dipole arrow, and it shows the direction the electrons go. So O is going to pull the electrons towards itself, meaning this will be slightly more, the oxygen will be slightly more negative than the carbon, but you can see they cancel each other out. It's a symmetrical shape. So even though technically it's not a nonpolar bond, there's definitely an uneven distribution of electrons in the bond. The whole molecule, that cancels out. Or if we look at something tetrahedral, so let's look at carbon tetrahydride or methane. So in this case, remember we have that 109.5 bond angle all the way around. This is a symmetrical shape. If I were to pick it up and rotate it around, it's got rotational symmetry. It's going to be the same in every direction. So even though it's kind of weird, like if you cut it in half, it might not necessarily be the same depending on which way you cut it, but it's got rotational symmetry. There's not one side that's going to be more negative than the other. Or even one, like a bigger molecule like an octahedral, that one, so if we had like an SF6, a sulfur hexafluoride, for example, it's a big shape, but as long as these are all fluorines on the ends, your terminal atoms are the same, then that is a symmetrical or non-polar molecule. So no lone pairs, all the atoms around the outside, they're all the same, because that means that even though if you have a polar bond, that'll all get canceled out because it's a symmetrical molecule. So then if we look at the polar ones, so these are going to be your unsymmetrical. So they might have different terminal atoms or lone pairs, or maybe both. So I'll show you a couple examples. Okay. So we just look like a really simple one like this. So this looks like our CO2, except we got fluorine on one end and we've got oxygen on the other end. So fluorine is more electronegative than oxygen. So that means overall this side is going to be more negative. So that is a partial charge there. Overall, that side's going to be more negative because fluorine is going to pull electrons to itself more than oxygen is. So different terminal atoms, that's polar. It's not symmetrical. The other version of not symmetrical, we could look at water. So water has this bent geometry. And it's got these two lone pairs up here at the top. So that bent geometry, it's not symmetrical. So water is going to be more negative up here at the top with the oxygen. So oxygen is already more electronegative than hydrogen. It's pulling those electrons towards itself. and then it's not getting canceled out by anything on the other side because it's not a symmetrical geometry. So that bent geometry is polar, which actually gives water a lot of the properties it has. It's polar and makes it a really special molecule. So anything that has these lone pairs and makes an unsymmetrical or asymmetrical shape is going to be polar. Now, I do want to show you an exception to that because there's always exceptions to the whole lone pair thing. So I could have a linear. So I'm just going to give you the EXX model that we use on our papers. So we have this, move it down a little bit. So we have this octahedral electron geometry, but it's got a linear molecule geometry. It's the last picture on your geometry sheet, and it looks like this. So it's got 4 lone pairs. So this guy is an exception to the lone pair rule. It has lone pairs, but it actually is still non-polar. So that actually goes over here to the non-polar side. So even though it's got lone pairs, it looks like it would be polar because it's got a symmetrical geometry, as long as these terminal atoms are the same. So as long as those terminal atoms are the same, then that is still going to be a nonpolar molecule. So again, nonpolar are your symmetrical molecules, polar are your asymmetrical or unsymmetrical molecules. You have to draw the Lewis structure to figure that out. So that's your first step, is you draw the Lewis structure. Once you've got the Lewis structure, you've got the geometry. You can do some work with that, but until you've got the geometry, you're not going to be able to figure it out. And that's polar, nonpolar.